Everybody, do you guys see my screen?
Yes.
Everybody, okay. Um, all right, so today we're going to be talking about some linear systems, and we're going to see how to solve them using graphs, okay? And the next couple of classes, we're going to see how to solve them by using other methods, uh, different than graphing, algebraic methods like elimination and substitution. So the past few classes we talked about lines and slopes and linear equations. Um, so today we will see how to deal with uh, linear systems. Okay, systems of linear equations, or also known as linear systems. Basically, what this is system is made of two equations or more. So at least two, for example, ax plus b y equals 6, and another equation, ax plus by equals c. Maybe some other numbers here, b1, c1. So previously we just talked about equations individually. We saw how to graph the equation, how to get the slope, and everything. Today we're combining both these into one system. So this is a system with two linear equations. Each one of these represents a straight line. So we're going to see how to solve this system by graphing. So when you take these two lines, we graph them in the same graph. The lines will either meet like this. In this case, this will be the solution, the intersection, which is basically a point. Okay, so we get the coordinates of this number. So this is, for example, line 1, line 2. If the two lines meet, we'll have one solution exactly, and the solution is the coordinates of the point of intersection. The two lines may never meet. Might be a situation like this where the lines are parallel. So in this case, no solution because the lines don't meet. Okay, so no solution here because the lines are parallel. Parallel. Okay, so no solution. As you can see, the lines never meet. The third case is when the two lines basically overlap. When you draw the first line and you draw the second one, you pretty much end up one on top of the other. So the two lines here, in this case, so the lines basically meet everywhere. Each point belonging to the two lines is basically a solution or a point of intersection. So in this case, we have many solutions, or infinitely many solutions, an infinite number of solutions. The lines overlap, we say. Okay, simply means that the two lines end up one over the other. It's technically the same line. When you draw them on the same graph, you basically end up with the same line. And that basically gives us many solutions. So that's basically how you graph, how you solve linear systems by graphing. In this case, one solution, like I said, intersecting. The lines intersect. Okay, so the lines intersect or meet each other. Here, they don't meet at all. They're parallel, so there's no solution. Or if you end up with, like I said, the lines being one over the other, so basically all these points, so you have many, you can say many or infinitely many solutions. So that's what the whole situation is all about. So first, so before we actually solve a problem, we're just going to make up a system. I'm going to check. We're going to have some given solutions, and we'll see if those solutions work for our system. So I'm going to say check in whether a pair is a solution to a system. Let's take, for example, the system here. X plus y 4, and I'm gonna need another one. Let me see actually here. Let me use a different one. So I'm going to take x plus 4y and 3x okay, as you can see, that's a system here, 2 lines, and these lines either meet, parallel, or overlap. Let's try some random. We're going to try a couple of pairs. If there is a solution, it will be in this form of a pair. So let's check 2 pairs. Actually, we're going to check maybe 1, 2, and then we're going to check another point, maybe 4 and -3. Okay, so 1, 2 is the first possible solution. So for this to be a solution, it has to work for both these equations. It has to satisfy this and also this. If it makes both, satisfies both, then it is a solution. If not, if it doesn't work for both, if it works for one and not the other, then it's not a solution. So this point here, this is a possible intersection here. It has 2 coordinates, x and y. That's what we need for the equations x and y. So we're going to plug both of we're going to plug this point first in equation 1. So if we plug x and y in equation 1 here, then we're going to plug it also in equation 2. Then see if it works for both. It has to work for both equations in order to get a solution. So for this one here, first equation is x plus 4y equals -8. So then substitute x and y both into this. So x is 1 plus 4 times what's y? What's y here in this equation if we plug it? So x is 1. 4 times what? What's the y based on this?
2.
Say it again?
2.
That's right. The 2 is here. The y is 2. So we're going to plug it here and see if it works. Okay, we don't know yet. So we try it here. Then we simplify. So we're going to start with the multiplication. That's 8 plus 1. And again, is it equal to -8? This is 9. This is not equal to -8. So as you can see, this does not work for this equation. So therefore, it's not a solution for the system because it has to work for both this and this. It didn't work for this. So even if it works for this one, it's not going to be a solution because it has to be for both. So there's no need to actually check the second equation because we already know it's not an equation, but let's do it anyway. Let's do it anyway. We're going to check this one again against this point and see if it works, just to basically practice how to check. So equation 2 is 3x plus 2y equals 6. Again, we check in with the same point. So we're going to plug x and y. X is 1, so it's going to be 3 times 1 plus 2 times y. Again, y is 2. And we'll see if it works. We don't know if it's equal, let's do that. So we have 3 here plus 4 equals, is it equal to 6? No, this is 7. Obviously not equal to 6. As you can see, this point does not satisfy both equations. It does not belong here. It does not belong here. Therefore, these two lines basically they don't meet. Okay, I mean, at least this point here, they don't meet at this point. Okay, this is not a solution to the system. In other words, the lines do not meet at this point here. Okay, so not a solution. This one, not. Now let's check the other point. So we have checked this one. Okay, so this one is not a solution. Now we're going to check the other one. 4 and negative 3, same thing. Again, this is x, this is y. So we're going to plug both in these equations and see, again, for this to be a solution, it has to work for both of these. We have to get equal here and equal in this one. So let's try that again. So equation 1. So we're going to plug the point into the equation. So x is 4 minus 4 times y. Here's a y, negative 3. And we're going to say, is it equal to negative 8? We're going to start from the multiplication first. Negative 4 times negative 4 times negative 3 is negative 12. We have 4 here. And again, we say, is that equal to negative 8? What's 4 take away 12? Everybody, what is 4 take away 12?
Negative 8.
Negative 8. And it's in fact negative 8. So that's good. So far, this works for equation 1. Again, in order for this point to be a solution for the whole system, it worked for this one, it has to work for this one as well. If it works for one, only one of them or none of them, it's not a solution. So let's check this one. Same way we did here, let's see if it works. So again, we're going to plug this into equation 2. Equation 2 will be in this one. So you have 3 times x. What's x again for equation 2? So we need x and y. Where do you get the x from? The x is here. Okay, this is the point again. We're still checking. It worked for the first equation. Let's plug it into the other one. So x is 4, and 2 times y. What is the y? What's the
Negative
y?
3.
That's right. The y is negative 3 here. And we're going to see, is it equal to 6? Basically, we plugged it here. We don't know yet if it's equal to 6. We need to simplify. So we do the multiplications first. So that's 12. Take away 6. Is it equal to 6? Yes, 12 to take away 6 is 6. 6. So what do you say about this point? So you worked through the first equation. You worked through the second equation. Is that a solution to the system?
Yes.
Exactly. So you worked for both. It is a solution. Which means this point belongs to the two lines. This point here belongs to the two lines. They either meet at that specific point, or the lines are the same, and this point that we checked happens to be one of those points. But that means it is one of the solutions. It's either the only solution or it's one of the many solutions. That's basically the idea of checking whether a given point is a solution to a system. So in this case, you will be given the system and you will be given the possible solutions to check. Okay, this is checking. Next step, we're going to see how to actually solve the system ourselves. We'll be given a system like this, no points, and we'll figure out whether the lines meet, the lines are parallel, or the lines overlap. So that would be the next section. Any questions so far before we move on to the next section? Everybody? You guys okay? Okay, so solving systems by graphing. So let's take first example here, maybe Y, another one. We have a system here of two lines. We don't know how they're going to end up. We don't know if there is a solution or not. So we're going to do this by graphing, meaning we're going to need to basically put both lines in the same graph and going to see whether the two lines either intersect or not, or overlap. So we're going to need a graph for that. Let me grab a graph from the internet. Yeah, you can easily Google a graphing paper and you'll get something like this. Choose one that has numbers in it. And you can use it to graph your lines. Instead of drawing a new line, you can simply find one online like this and use it. Okay, so we're gonna graph both of these lines here and see how they behave. Let's call this one maybe line 1. This is line 2. So to graph this, as we saw previously in the previous 2 or 3 classes, this is the what we call the y-intercept. This number here is the y-intercept. And what do we call 2? Look at this equation here. What do we call the number 2?
The slope.
Exactly, this is the slope. When a line is in this form of the slope form, this is the slope form basically. It's the what we call the y-mx form, mx plus b. This is the slope, this is the intercept. When it's in this form, it's very easy to graph. You start from here, and then you go to the slope. So first, you got to start from the y-intercept. This always can be found on this axis. This is the y-intercept. I mean the y-axis. This is the x-axis. So to graph this, you got to start from the y-intercept, which is always found on the y-axis. So it's going to be right here. It's -3. And from that, we're going to go to, so the slope is 2 or 2 over 1, which is also called the rise over 1. The slope here, if it's not a fraction, you can put it over 1. So you start from here, then we're going to go up because this is a rise. For the rise, we go up or down, as we saw previously. And for the run here, we either go right or left, depending on the sign of the number. So again, start from here. This is a slope, so we're going to go up twice from here, 1, 2, and then to the right once. So this is either up or down. This is either, so this up or down. This number here is either right or left. If it's positive, we go left. If it's negative. For this one, if it's positive, we go up. If it's negative, we go down. Again, we discussed this in detail in the previous lectures. You can go back to the videos and rewatch them. So start from here, go up twice, and go up twice, and go to the right once. Start from here, go up twice, 2 units or 2 squares here, 1, 2, and then to the right once. That's it. That's our first line. We have 2 points. The y-intercept, rise up 2 to the right once, and that's the line. Let me grab it. So we're going to need a straight line for this. Okay, it's better to use a ruler here. And that's basically our first line here. Let's call this line 1. Okay, so far we're done with the line 1. So we're going to repeat the same process for line 2 here. And we're going to see where it lands, either like this or parallel or on top of the other one. We don't know yet. Let's find out. Okay, so again, that's the line 2. So where do you start from to graph this line here? What's the first thing? What's the first point you plot on the graph? So again, we always start from this point. Again, this is what we call the y-intercept. And the slope here, or m, slope is always next to the x. M is -3/4. So now, where do you find the point here? This y-intercept, what exactly would you find it on the graph? It's called the y-intercept, so it's going to be on the y-axis. It's going to be here. It is a positive number, +1. So here is +1. Okay, or simply just 1. Okay, so we will locate that number first on the y-axis. It's always going to be on this axis. And now we're here. So where do you go from this point based on the slope? Where do you go next? So we're here, this point. So what do you do next? If you look at the previous example, we're going to do the exact same thing. You start from here, and then this is the rise. Okay, the rise over run. So the rise is either up or down depending on the sign. Are we gonna go up or down for this rise for -3? Are we going up or down?
You're going down.
That's right. Why?
Because it's negative.
Exactly, because it's negative. So we're gonna start from here. We're gonna go down 3 units. After that, this is the run. The run is either right or left. So where do you go with the run with 4?
You go right.
That's right. It's positive, so we're gonna go right. Start from here. We're gonna go down and then go right. We start from the y-intercept, which is here. So we're gonna go down 3 units, 3 squares, 1, 2, and 3. Then to the right 4 units, 1, 2, 3, and 4. And that's basically the second line. We start from the y-intercept, go down 3, 4 to the right. Let's draw that with a different color. We're gonna need, it's gotta be a straight line. We need the ruler for that. No, it's not gonna work well. Let's try again one more time. So that's gonna be something like that. That's our second line, and it's line 2. And based on, so you see how the lines end up. So which case is it from here? How many solutions do we have? Is it 1? Is it none? Is it many? So how many solutions do we have for this problem? So again, look at the lines here. We put them on the graph. How many solutions are we going to have based on these scenarios? Is it going to be one solution? Is it going to be many solutions? I mean, no solution, or is it going to be many solutions? What do you think? You see how the lines are on the graph? They'll look like this. Are these lines? Do they intersect? Do they are
You
they
said
parallel?
if the lines are parallel, if they have any solutions.
So if they're parallel, no solution. If they intersect, there's one solution, which is this intersection. Or if the lines overlap, there's no solution. So which case is it here?
It has a solution.
How many solutions? Just one, right? This intersection is basically the solution. So that's the solution. And you just try to read approximately the coordinates of these points. Right? It's from the graph. You don't expect it to be 100% accurate, but you're going to see approximately. So here we have one, here none, and here we have many solutions. So in this case, we have one solution. So what do you think? What do you think the coordinates for the points are? Let me erase this line here. So start with the x. Approximately, what is the x of this point here? What is the x? It's between 1 and 2, it looks. It's approximately 1 over 2. Or 3 over 2. That's approximately 3 over 2 or 1.5. Okay, as you can see here, the 1, 2, it's about in the middle, close, but it's about 1.5. What about the y? What's the y on this point? It's between what values? If you drop the point on the y, what is the y approximately here? It's between 0 and -1. So it's about 0.5. Okay, so that's how you read the solution approximately from the intersection. As you can see again, to find the x, we drop it over the x. It's between 1 and 2, it's about 1.5, 1.5. Then you drop it over the y-axis to find the y coordinate. It's about a half, or actually a -half. Let me write it again here. So this is -0.5 here. And basically this solution is, that's our solution for the line, for the system. It's specifically that intersection there where the lines meet. So that's what we mean by solving systems by graphing. You gotta graph both lines on the same graph and see which case is it from these three. If you're lucky, if the line is in this form, y by itself, mx plus b, it's quick and easy to graph. Start from here and do the rise and the run. Start from here, rise and the run. If it's not in this form, if it's in standard form, then you'll have to do a table of points, as we're going to see next. Let's do another example where the lines are not in this form, not y by itself, but we have y and x on this side and a number on the other. We're going to see how to solve that using graphing. So, okay, and another example here. Take a system and let's take this system here plus. Okay, so that's a system of two lines. As you can see, they're not in the y-mx form. This is what we call the standard form. And when lines are in standard form, so we can't use the rise and the run right away, unless we change these into a form like this, or we need to use what we call the intercepts. We talked about this before, so we're going to need a table for each line in order to graph it. So we're going to need to graph line 1 and then line 2. So for each one, we're going to need a little table with X and Y, and what we call the X and Y intercepts. So we're going to put a 0 here and a 0. This pair here is called the y-intercept. So the y-intercept is basically when the x is 0. So this point is called the y-intercept because x is 0. The other one is called the x-intercept because the y is 0. Now we just need to complete this table, find these two values, and we should be able to graph line 1. After that, we're going to repeat the same thing for line 2. So now we're working with line 1. Again, you start with this table, put zeros here. Just need to find this value here and also this value. So this is line 1. It's this one here, x plus 1, x plus y plus 3. So to find the missing number here, we know the x, which is 0, but we don't know the y. So we're going to take the x, we're going to plug it here, so it'll be 0. And we don't know the y. We're going to find it after we substitute, so y equals 3. As you can see, 0 plus y is y, the 3. So the missing point here is 3. Okay, so we have 3 here. Now we're going to repeat the same thing too. This is 1 point now. This is 1 point. We can graph it on the graph like this later. You just need to find the other point. We're going to graph it, and then we're going to join them together with a line. So let's complete the other pair here. So we know that the y is 0, but we don't know you're missing the x. So what do you do here to find the missing number? So what do? We know the y, we need to find x. Again, we're going to plug the y here. The y, we know it, so we're going to plug it in the equation again. This is the equation again, line 1. This time we know the y, which is 0, but we don't know the x. X is missing, so it's going to stay here. We solve x plus 0 is x and 3. So the other point here is 3. So we're done with line 1. Now, with this information, we're able to graph this line. We're going to repeat the exact same steps with line 2. Once we graph both, we see how they end up on the graph. So let me put this in a graph now. Let's put the line 1 in the graph and then do the same thing for the other one. Okay, so this is the graph again. We're both going to end up here. Okay, so the first line 1, we have 2 points, 0, 3, 3, 0. Where do I find, or how do I plot to this point here, 0, 3? How do I do it on the graph here? Where do I find this point? To graph 0, 3, so we're going to start from x, which is 0. And we're going to go up to 3. So start from 0, 1, 2, and this is 3. That's this point. Then we go to the second one. This time we're going to start from 3. So x is 3. Then we're going to go to the y is 0. So x3 will be here. So this is the x-axis. This is the y-axis. Start from x, which is 3 over here. And since the y is 0, we're not going up, we're not going down, we're going to stay right here on this graph. So 0, 3 is here. From 0, go to 3. And 3, 0, we're going to start from x3, which is here. And the y is 0, so we're going to stay here. We're not going up or down unless we had a positive or a negative number here. And that's basically it. That's the first line. We can go ahead and graph it. Okay, so that's line 1. And now we're going to see, we're going to repeat this again. Pay attention to this second way. We're going to do this. We're going to do it just like we did. And once we complete this line, we'll put it somewhere here, somewhere on this line, and we're going to see how many solutions. So the exact same process. We're going to need a table. So X and Y, again, put 0 here, and find the other numbers. So you're going to find this one, find this one. Once we complete this table, like this, we're going to plug the points here and get the line. So again, we're working with line 2, so we're going to be using this. So 2x plus 2y equals 6. So the first thing is we have x0, nothing here. We're looking for this. So x0 is going to go here, 2 times 0 plus 2y equals 6. That cancels, so 2y equals 6. If you divide by 2, y will be equal to 3. That's the missing number here. Let's do the same thing again, this time with this point. This time we know the y, but we don't know the x. We know the y, so we're going to plug it here. Then we're going to solve for the x. So it'll be 2x plus 2 times y, which is 0, equals 6. So that cancels. So 2x equals 6. And again, divide by 2, so x will be 3.
It's going to be graphed with many solutions.
Exactly, because it looks like it's the same points. The line is going to overlap. That's right. The line is going to overlap. It's going to be the same line. Therefore, we have many solutions. That's exactly the point I was trying to make here. So as you can see, it's the same table again, 0, 3, 0, 3. So it's going to be the same point again here. And we have 3, 0, 3, 0. It's also going to be here. So we already have the green line. The red one is going to go right through those points also. And we have ourselves maybe a little to the right. So these two lines, as you can see, they overlap. So that's right, we have many solutions. So the lines overlap. Therefore, there are many solutions. Or you can say infinitely many. Infinitely many solutions simply means because the lines don't stop, the lines keep going in both directions. So we have infinitely many solutions because the lines basically extend in both directions. So many solutions, technically the same line, so all basically they meet everywhere. Each one of the lines, each one of the points is an intersection, including these two that we found here. And again, if your lines end up like this, totally separate, no intersection. If you graph them in the same line, for example, and one line ends like this, the other one like that, so that's when you know you have no solution because the lines will never meet. So the solution is basically the intersection of the lines. It could be one intersection, could be many. If there is none, then there's no solution. So there's two cases you may have the lines in this form, YMX form, intercept, horizon rhyme. That's convenient. You can plug those right away. Or if it's in standard form, then again, start with these two tables. Start with a couple of zeros here, find the other numbers, put the numbers in the graphs, and see how they end up. We discussed this in detail in the previous lectures. We saw how to graph this type of lines, also this type of lines. We did it again today, but if you still have questions about it, you can go back to the previous lectures and review them on details. Okay, so this is line 1, and line 2 is the red one. And that's basically how you graph lines using, how you solve systems using graphing. Like I said earlier, we're going to have 2 other methods of solving this without the graphs, just solving equations. So algebraically solving linear system. We're going to learn that in the next couple of classes. Let me see if we can do. Any questions, everybody, about any of these problems so far? Everybody, any questions?
No.
No, Professor.
Okay. Let's do one more here. Again, I'm gonna go back to this form here, a YMX form. Okay, we have these 2 lines. Let me paste the graph. So same thing here. We're gonna graph these quickly here. Where do we start from again? With a form like this. If I want to graph this line, what exactly do I start? Which point? So as always, if it's in YMX form, start from here. Positive 3 is right over here. Then the rise on the run. The rise on the run. So you're going to go down 2 units and then to the right once. From here, go down 1, 2, and then to the right once. That's the first line. Okay, so line 1 is done.
Wait, Professor, why do we have to make that the first line? Why do we have to make the negative 2x a fraction?
Because when you do the rise on the run, you start from here, then you want to do the rise on the run.
Okay.
So we need both of these. If you don't have it, you can put 1. But for this one, we already have it, so we don't need it. Okay, so this is negative 2 over 1. So that's our first line. Now let's do the second one. Where do we start from again for this one? We always start from where to graph line in this form? We start from the y-intercept. Okay, again, this is a slope. And this is the y-intercept. We'll always start from here. So we're going to start from negative 4, which is here. It's going to be on the y-axis because this is the y-axis, this is the x-axis. And for this one, what's the rise on the run here for this one? So the rise is invisible 1, and the run is 1. So 1 over 2. Start from here, go up once, and then to the right twice. Start from here, go up once, to the right twice. And looks like our line is done. And that's about it. This is line 2. How many solutions do you have here? After graphing these 2 lines.
Just one.
Just one solution. That's right. It's right here. Approximately approximately here. What's the solution here? This is the solution. We put it in blue. What's the x and y approximately here? The x is
3,
that's right, and
3, -2.
that's right, close to -2. That's approximately -2. So that's our solution here. And it's the same process every time, basically. So you just have to graph both lines and find the intersection. Any questions, everybody? Before I give you some practice to do on your own. Okay, let me give you a couple of problems to do on your own here. Okay, check. So check whether, give you an example whether what is it? So we're going to check this point, plug it into this system and see if it's a solution. And also, we need to graph, well, solve by graphing. So solve by graphing this system and another one here.
You want us to put all 4 lines in the same graph, or you want 2 different graphs with each with 2 different lines?
Do a graph for each system. So this is
Okay.
one question. This is another one. So system 1, system 2. Okay, and this one just check for the solution. Actually, let me change this a little bit. Just this one, I'm going to change it a little bit to this. -2x plus y. So use these instead. So one is in YMX form, the other one is in standard form. So you need to know how to graph these. This is standard form, this is YMX. Again, just like we did earlier, just follow the same steps. I'll give you a few minutes to work on this, and then we'll check with you afterwards. All right, so What did you guys get for the first one? Is that a yes or a no?
Yeah, it's a solution.
That's right. So this is yes. Just plug them here. It works. What's the solution here? What is the approximate solution for the system here?
I got approximately 1.5 and 0, comma 0.
1.5 and 0. Let me check. Probably, let's see. So this should be approximately here. Yeah, about 1.5, I think, yes, 6. That's close, that's right. So 1.5, 1.6. And negative. Yeah, it's pretty much very close to 0. 0, we'd say 0.09. So that's good. That's a pretty good solution. What about this one here? Second one. Anybody did the second one here?
No, I haven't done that one yet.
So this one we do it the same way we did this one here. Exact same way. We're going to need two tables. First, graph the lines. And here, the lines should end up parallel. No solution. Okay, so if you do this later, they're going to be on the same graph, but completely, they don't meet at all, so there will be no solution. And that's pretty much how you solve linear systems by graphing. Like I said, we're going to learn two other methods next time that do not involve graphing, and they are more accurate because we use equations, algebraic methods to solve. Everything we saw here today